Welcome to my to this webinar in May 2022. Just fixed that on the fly. Typo on the cover sheet. Welcome to the first part of persistent storage analysis. Now we have talked about in the past about persistent storage acquisition, and Klaus has talked about memory forensics and so memory analysis. So we'll complete this series by this talk, or by this and the next talk, talking about persistent storage analysis. Now, part of this talk will sound familiar. What will we cover today? Hopefully, so we'll talk about the general ansatz of what to do once you have an actually acquired an image. And we'll look at some simple cases. We'll take it simple from here for starters, not to overwhelm anybody. How to look for, first, how to access image files sensibly. Then how to look for, what to look for, and actually how to look at suspicious files. Finding the needle in the haystack, looking at the needle in the haystack. And we'll see how difficult that is actually. And then we'll briefly look at how to discover some hidden or lost data. And then, of course, I'll point out from my stuff from my perspective is interesting and treacherous if you are not mindful of those things. So things to watch out for that might trip you over if you're not careful. As always, in the end, we'll have the opportunity to ask questions. As always is, of course, a little euphemistic. I hope that I will stay within the time, but we'll see. There's going to be some demonstrations, but also some slides as well. So the usual word of warning: we're not lawyers. If you suspect anything legal, any legal action perspiring from any particular incident, step back, go talk to a lawyer. You've seen me show this slide plenty of times, so let's not waste too much time on that. The prep remarks and the introduction actually also should look familiar if you have attended my previous talks, because it's essentially, of course, the same considerations that also govern how to approach imaging data and acquiring persistent data. Those same, or at least very roughly the same similar questions and guidelines also govern, of course, how to analyze that. So this is shamelessly stolen from my last presentation, and because of that I will, because of that I will skim over this fairly quickly. So the bigger picture is, so there's some sort of persistent storage that you would like to analyze. This has not changed from the last talk, and what has changed is that you have actually acquired the image. What kind of storage are we talking about? What size, where is it located? We will, for this talk, assume that we're talking about a local full disk image file. You might, of course, acquire images just by partition or just get files or whatever. But for this purpose, for the purposes of this talk, we'll assume that you have a full disk image file that's locally, and we'll also assume it's fairly small, so we can actually handle it real time here. The second point is actually more important. What's the point of actually of the analysis? What's the point of the whole exercise? This turns out to be a key thing to consider, preferably before you start, because depending on what your aim is, you might ask for a lot of work or not a lot of work. Either way, knowing where you want to end up helps a lot in deciding whether you're already where you want to be. So defining a condition that once met will allow you to say, okay, we've done enough, we've done what we've set out to do, so we're now done and will not waste any more time. Because as you'll see, you can waste plenty of time in any forensic analysis. And of course, how safe do you want to play this out? As in, do you want to actually destroy any data accidentally, or do you want to take the chance of that happening, or do you want to accidentally expose data? Of course you don't, probably. So This again has not changed. Mass storage devices come in many different shapes, ways, or forms. Usually there's some structure in there that goes in the way of partitions or file systems or RAID volumes or virtual images. And data can still, as in last talk, be hidden in any of those layers, either on purpose by some attacker, or just by coincidence, so to speak. For instance, the typical example of this would be deleted files, in which case you would only have access to those files if you look at the actual underlying block device. But data can also be hidden in plain sight, meaning that your typical file system contains, well, probably hundreds of thousands of files, if not more, depending on your actual system. Certainly sometimes way more than that. So if an attacker decides to hide something in a particular file, then, well, it's technically in plain sight because it's not hidden, but you have to know where to find it, right? And it's not possibly not that easy to identify those files. As I mentioned, so it's from each layer in the file system, in the storage device, it's there's some slack space at the end of files. There's files are not usually aligned with block sizes, so in the very last block of a file, there's usually some slack space that cannot be accessed by accessing the file, but can be accessed by, for instance, looking at the block device. This is one of the places that an attacker might decide to hide data in. The examples I already said: unallocated data, space in volume groups, space between any structure, boundaries and non-aligned data, deleted files. And there's also interesting metadata sometimes to be had in lower layers. For instance, in file system superblocks, there may be interesting, not even explicit information hidden. But we'll come to that later on when we look at some characteristics of file systems and timestamps. So all said, it is still advisable to actually analyze the data from as low a layer as you can possibly manage, knowing that this is a trade-off, of course. Yeah, and obviously, the larger an image is that you want to analyze, the more pain it's going to be. In terms of where to put it, it's not as easy to copy around if you need backup copies, if you want to store samples, whatever. It will also take more time to analyze, because that is just the way things work. If you consider more data, then, well, obviously you're going to take a longer time. So this is again crucial, a crucial factor when it comes to determining, okay, I've spent enough, I've wasted in quotes enough time on this particular analysis. So that's something you need to be wary of. You can't spend an infinite amount of time going through those gazillion files on the file system, and the larger it is, then the more likely it is that you will overlook stuff. But how much time do you want to spend on that? A week? A month? I mean, there's really no limit to that. So this is crucial. And so this means that if you can limit the scope of your investigation right from the start, then you'll save yourself a lot of trouble. Obviously, it's not usually that easy, or many times it's not that easy, but use all the information you can get to limit the possibility. And finally, as for general observations, of course, play it safe in terms of make sure that you don't accidentally delete data. I've already said this many times. This is still the same as it was before. So this is all still true. So let's go and dive in. I have sort of structured this talk from the lowest effort, lowest threshold investigation mode up to most effort, most thorough, most comprehensive analysis mode. So what this means is that the stuff that I'm going to talk about sooner is likely going to be the stuff that is useful for, let's call it triage, for want of a better word. So for some initial, very rough analysis to decide whether it is fruitful or interesting, or what do you want to call it, whatever you want to call it, to worth your while to dig in deeper and put more effort into this. Having said that, this is already one of those crucial steps, as whenever there's drawbacks to everything of these, to all these steps here. So having said that, be aware that whenever you decide that, oh, look, this is going to be interesting, this is going to be, say, a legal case, this is going to go to the police, then maybe even these initial steps are too intrusive. So at any point in time when you decide that stuff needs to be taken to a higher level or to a higher standard, then always consider the option of, well, okay, then maybe I shouldn't be doing all that other stuff that I'd possibly like to do and I'd really be interested in. And look, it's in this talk, so I could do that, right? But maybe not. So just consider it, keep that in mind. So obviously, the first thing that we need to do is somehow access this image file. And we'd like to do this as quickly and as painlessly as possible, and with as little effort as possible, as I have just outlined. So the obvious solution is, right, we're admins, just mount the image. The central advantage is, well, yeah, you don't need any additional tools to do that. Many times you can just take the image and mount it on your local, let's say, desktop or forensics machine or whatever, on your local machine where the image is available. The devil, however, obviously is in the detail. There's many things that can trip you up here. And I'll assume that, well, of course, you need the proper drivers for the underlying file systems and all that stuff. Obviously, you need supported, if you're talking about image formats, then you need to be able to read that image format. Hopefully, you'll be able to do that. You might need to reassemble stuff if you have images in the form of, say, flat files that actually need to be reassembled as a, say, RAID volume. You might have to, and we've talked about that as well, you might have to decrypt stuff because your image happens to be an encrypted block device. So all of that nitty-gritty detail, we'll just ignore that for the moment, as we want to keep it simple. But keep in mind that that's all that good stuff might trip you up. In general, you want to avoid mounting your images read-writable for obvious reasons. So the way to do that, obviously, is to use the read-only parameter for the mount command. However, I strongly suggest to, in addition to using that parameter, or as we'll see, that is not really necessary then, but in any case, multiple layers of defense, right? So in addition to that, I really recommend making your image file read-only as well. And in fact, what I personally like is to not only make it read-only, but also make the file immutable. This has the advantage that even the root user cannot, by accident, delete the file or overwrite it or whatever. And in many cases, we will actually have to work as root if you want to mount partitions. So there's the real danger that that you might mistype. So just by making by making, and hopefully you can see my screen now, just by making an image file read-only and immutable by issuing this command. You can go a long way. Of course, this is not permitted unless I do a sudo. But now you cannot delete, you cannot move, you cannot rename, you cannot do anything with this. So that's something. So that's exactly what I've just showcased. You can also take away, and I recommend again, both of these measures, just his suspenders and belt, right? Do both of this, take away the write permissions, and then make the file immutable. Of course, the order is important. Now I cannot do the change mode anymore. So how do we handle the one big the one big stone that we can trip over now is partitions. If you have a flat image of a raw block device, then it's likely to contain partitions. And the way to deal with that is, well, my personal view is that this is something that you should take the foolproof way, and that is to use KPartX, which is a part of the multipath tools in many distributions. So if you don't have that installed, then I strongly suggest installing that. This is very, very useful. So what KPartX it will take an image file, and if you tell it to actually add partitions, then it will just scan the image file for partition tables, and if it finds partitions, then it will create some loopback devices and map loopback devices, so you can actually access that image, that given partition that it has detected. The way it looks is again this. So KPartX, add verbose and read only, and let's take demo image. And again, I cannot do that. Obviously, I'm not root. So there you go. So now what has happened is KPartX has scanned this demo image file. This, by the way, is really, really small. This is just 4 gigs. So things will be reasonably fast. Fortunately, with Linux images, you can strip them. Even these days, you can strip them fairly far down. With Windows 10, for instance, it's not as easy. Either way, so KPartX has created those block devices, and now it even tells you the names of the devices that it has created. So there you go. I can obviously remove those, delete those again, and now they're gone. But if you have those, you can then, if you add those, you can then just use them as a regular block device. And I should really do that. And then we run into problems, as we will see in a minute, because this is a dirty file system. This is one of the problems that you might run into. We'll cover that in a bit. More basically, of course, you can, if you prefer, not use KPartX, but look at the partitions that are on this on this image file by hand, so to speak. So you can run fdisk or sfdisk or cfdisk or whatever gpart add. Let's take fdisk and list all the partitions in demo image.raw, and totally surprising, KPartX and fdisk agree that, no, look, there's partitions starting at there's 2 partitions, one starting at sector 2048, and the second one starting at sector whatever 7 million yada yada. So that's good, I guess. Now, if you want to go the manual way, of course, then you need to mount the partition manually, which means that you need to calculate this nice offset. Mount can mount the mount command in Linux can actually mount images starting not at the beginning but at an offset. As you know, So then you need to take the starting sector and multiply that by 512 in this case, right? Then just multiply that, and you can mount the partition the same way. Then, of course, just to make matters complete, you can always just copy the partition into a separate image file with, say, dd-rescue. This is one of the instances where what I meant earlier comes into play. This may be a good idea if you just want to copy around this partition to somewhere else, or if you just want to import that particular partition into some tool or whatever. You can severely limit the need in bandwidth and storage by limiting what you actually do and by limiting what you actually look at. So if you know for sure that you're only interested in, say, the boot partition or the whatever, the root partition, but not the home in this particular demo image, everything is in one place. So this does not apply. But in principle, you tend to have different partitions for /home and // and /boot. And so you can, if you know for sure, for whatever reason, that you actually only want to look at /boot, then yeah, just use that image. And then if you want to import that into tools that can only handle full partitions, then you obviously need to copy that out. So that you can do that with this dd-rescue command. For instance, you can do that with dd or many tools, but dd-rescue is a very nice tool for that. This has one caveat though, that you can, this is another thing that might, another one of those nitty-gritty details that might trip you up. So you want to start at the offset in bytes. This is what you tell dd-rescue with the -i parameter. So you want to start copying at whatever offset your partition starts at in bytes. So not in sectors, but in bytes. Essentially the same number that you have calculated here. And then you also want to specify at what position in the output file the copying process should start. By default, dd-rescue assumes that if you start the reading at byte 10, for instance, then you surely want to start outputting at byte 10 as well, right? So that means that the first couple of bytes will just be filled with zeros by dd-rescue. It tries to be helpful there, so you can recopy if you can restart your copy process if something breaks on the way. But in this case, this is not what you want. In this case, you want to start the actual file, the actual copied new image at byte 0. So you need to tell dd-rescue this. So this is something you can trip over. And then you just specify from where to where. And so there you go. So and so now let's have a word on this, why I couldn't mount this. Let me, for demo purposes, reinitialize that. So it tells you, oh look, you can look at in dmessage, and there you go. So this file system I have actually imaged for this demonstration purposes. I've imaged from a running machine, which means that it's inconsistent. It's an ext4 file system that has been grabbed and yanked out of the running machine, which does not work, which generally Linux will barf at. So be aware that there's some inconsistency here. You can obviously not write to it, but you can mount with no load. You can also, if you prefer that, make your image read writable. And I strongly discourage you to do that, but you can in principle, and then just mount it, read writable, and then the journal would just be replayed and you'll be good. However, let's just, for demo purposes, use no load. My bad. And there you go. Now it's mounted without any problem. So now that we've mounted stuff, first things first. I've already mentioned this before. You want to use any information that you can possibly can gather on the system you want to analyze. This means any hints whatsoever that you might have get your hands on regarding what is wrong with the machine. Presumably, there is a reason that you actually want to look at the system, at the image. So presumably something has gone wrong that you want to investigate. So the more you know, the more you can figure out right from the start, the easier it will be for you to find the cause or get down to the actual root cause of the problem. Think things like, oh, look, somebody told you, preferably your security people, there's connections going from the system to known bad command and control servers. So you want to have a look there. It might be malware infested. Or some user complains that there's this weird process that I don't know what it does, shouldn't be using 100% CPU load, but it does. Maybe it's a miner, a Bitcoin miner or Monero miner, I'm sorry, whatever. Or for instance, you get a report that, oh, look, there's many HPC sites or a number of HPC systems now that report having been hacked, and people see rootkits in, say, to name an arbitrary example that may or may not have happened, in home users and user home directories .mozilla/plugin/.aa. And just as an example of this, consider this totally unrelated KIT-CERT advisory that gives you, for instance, oh, look, here's incidents, and oh, these things have been observed in other places. I believe there is a question or something. Okay, yeah, of course. Hello Setup will of course do the job. There's many. Oh, I should have mentioned this before. This is not the one and only way of doing things. You can skin the cat differently as well. This is just one example of what I think is a good approach. If you prefer other approaches, then that's totally fine. So anyways, the more information you can get on your system, on the system you're looking at, then the better. And if you have information, then obviously take a look at those leads first. If you have been told, oh, well, look, you're running an HPC site and people in the HPC community running your exact brand of clusters report they've been hit and people have put this weird file in users' home directories, then by all means go and look if you have those files in your file directory and in your home directories. There's no point in wasting your time doing general analysis unless you can actually, if you actually know there's specific indicators of compromise that you can go look at. So if you have, this makes your life so much easier. So at least you can confirm that you're hit with the same problem then in that case. Barring that, you need to wade through the entire haystack. There's some basic sanity checks that I recommend if it's available. For instance, there you can run your package manager if there's such a thing installed and usable. Interestingly, not usable in all cases, but if it works, it's great. You can use your package manager to verify that all the installed files in your file system actually match what the package manager thinks they should look like. This is done by running hash sums, of course. And of course, be aware that if an attacker is sufficiently sophisticated, then of course, if he can change system files, then he can change hash sums as well, right? So you might need to dig deeper into that. But if you find something that's this is a typical problem of a semi-decidable thing. So I have a Debian system here. So let's just still have this mounted. So let's just give it a go. Change root into that, and then just deb sums. Yeah, and there you go. This just goes over all the installed packages and spits out the, obviously this is not feasible, but then, you know, just fgrep for failed. Ignore the language output, and there you go. One file is reported as, no, this doesn't have a matching checksum, which is in fact totally correct. I fiddled with that binary just for demonstration purposes. RPM has the same thing, RPM verify all. This obviously only covers all the data that the package manager, all the files, excuse me, that the package manager has data for. And then there's well, the set of suspect files that you can, you know, well, when you build up experience, you come up with your own personal heuristic of, this looks suspect, or this is weird. So one of the first things I like to do is find stuff that has the setuid root bit set, which is, as a first approach, can be found with this nifty little find command. So we can demo that as well. So sudo find mount dash permissions dash 0400, and then you get a list of files or directories that have 0400 set. That is already smaller than the rest of the system. This is just 49,000 files, so it's close. It's getting better. So others is that I've personally found very helpful to look for is looking for directories or files that start with a dot, with a period, and then a blank, or period blank, or period. And to do that, this for some reason people like to hide stuff in these directories, because anything that's starting with a dot is not listed in standard lists, directory listings. And then I guess the argument is that, oh, if I call my file period blank, then if you just do an ls-r -a, then, well, it'll just, you know, there'll just be two dot files, and people will overlook it. Maybe that's true, maybe it's not. Either way, the way to find this is, again, this find. Another thing to look for is interesting places with a bash history that shouldn't really have a bash history. That's something that surprisingly many attackers overlook. So for instance, if an attacker manages to log in to, say, the XIM account on a mail server, then all of a sudden in XIM's root directory, there's a bash history if the attacker calls a bash. That shouldn't be there. So that tells you right there that something fishy is going on. Same thing goes for SSH keys in interesting places where they shouldn't belong. So if you're provided your web server is your SSH server is configured in a standard way, then you can just look for .ssh directories, because the web server will SSH server will look for SSH authorized files, authorized keys files in the home directory /.ssh. So if you find that for system users that shouldn't really have that kind of stuff, then that's a red flag as well. Another favorite of mine is look for what users actually have passwords set. You'd be surprised at how many script kiddies try to just set a password for say the LP user, line printer, that just shouldn't have a password. So they have a backdoor to a system user, that kind of stuff. And of course, this is, by the way, 4 examples. I've written down 4 examples for a reason there. This is not exhaustive, and no list can ever be exhaustive here. So whatever is the stuff that you come up with your experience, that's the stuff to look for. This is just a short list of what I usually look for. So obviously, moving on then, there's the usual suspects that you want to inspect. So log files that you obviously have centralized, right? I mean, you have central logs, so you don't have to look through local logs. In the remote chance event, in the off event that that you actually don't have a centralized log, well then yeah, go ahead and look at the local logs a little more closely. If you do have centralized logs, then it might be worth comparing what the local system thinks its logs look like and what your central system thinks its log looks like. Because if an attacker manages to break in, and he'll likely, more than likely than not, try to change the logs to cover his tracks, then obviously the central logs will not be altered. So if you have discrepancies there, then, well, that might be worth looking at. Same goes for audit traces. So if you happen to have Linux audit mechanisms running, that's a good thing. It's a ton of data to wade through, but it might provide excellent and split-second precision of what an attacker did or did not do. I've personally worked in one case where this was enabled for accounting purposes on an HPC login cluster login node, and that was tremendously helpful. We could, down to the split-second, pinpoint what the attacker did and when. Unfortunately, it turns out that the audit file, at least the format used back then, only stores the first, I believe, 16 bytes of every command line. So that was chopped after the first 16 bytes, but hey, better than nothing. And then, of course, the critical binaries. This is, again, a matter of fluid definition, a matter of experience. So candidates that I usually look at are the SSH server and client binary. The server often contains, if you have a compromised system, the SSH server binary contains a backdoor, while the SSH client, on the other hand, sometimes is replaced by one that actually logs passwords and stuff. The way to do this, usually or many times, these backdoors write for some reason to the credential information into files in the /user/include/linux tree. So looking at these files might be interested in, and you can easily look at who owns those files in the directory. And actually, every include file should, in that system directory, should be owned by some package. So if you find a file there that is not owned by any packet, then that's a red flag as well. Also, you can just inspect your binaries with strings. It's as easy as that. So let's just do that. Remember that because strings tries to be helpful, it'll only look at certain ELF file sections, but you actually want to look at the entire file here. So you need to add -a and look at that. There's a reference to this interesting file here that doesn't really have have anything to do with SSH. So for comparison, the SSH in my uncompromised system doesn't have that. So one might have a look at that. Once you have identified something like that, you can have a look at it. Oh, it's a binary file. That's interesting. Gibberish. That doesn't look like a header file. So then here's next bit of experience. Turns out that many times the people just XOR stuff. So look, we can use CyberChef, use the XOR brute force method, and then I've already moved to the correct directory here to upload that file that we've just found. And lo and behold, it's just been XORed by 0xFF. So by all bits 1. This is not uncommon, which is exactly why I picked this example. So if you ever come across anything like that and can make sense of it, just keep that in mind. Cool. And of course, malware tries to be persistent, so keep that in mind. There's many places there's a lot of places to achieve persistence, but have a look at the common ones, which is init process data, etc inittab, etc rc.d, initd, the init scripts, whatever your locally used init system is. Systemd has its own completely separate ecosystem. Look at cronjobs, user cronjobs. Keep in mind there's user cronjobs, there's system-wide cronjobs, there's scheduled tasks that run hourly, daily, weekly, monthly, or something. And of course, have a look at any services and binaries that are ubiquitous. As in, if you run a web server, then it's not been unknown that advanced attackers just add their own web server modules to Apache or even to Nginx. So have a look at that. Be mindful of that as well. Having said that, this is all. Remember, this is all the mounted file system. If you want to avoid that for whatever reason, you can use other tools. This gets more specific in that you need to have those tools. It's not much effort to install those. They come with many, at least test disk comes with many, if not all, distributions. So this can take an image file and scan the image file and gives you a walkthrough ability through all the partitions that it has detected. It can even detect deleted files in file systems. And then there's a corresponding utility called photorec, which will do full disk carving for some file formats, mostly, as the name suggests, images, but also some others that might be handy. Just as a quick that's what it looks like. So you can analyze it and comes up with the partitions. Doesn't find anything because I took the wrong file. Silly me. So there you go. And there's partitions, and you can list files and browse through files and stuff. So that's immensely useful. And you can then copy files out of this. Cool. So now that we've gone through these basics, we've decided to go take things to the next level and take a more comprehensive look at the system, which means timelines. Generally speaking, timelines are a huge dump, linearly sorted of a huge dump of events, a single place of all events that happened on a system, on a given system that you want to analyze. Data sources for this are the file system, potentially, most certainly, log files, any other timestamp data, really, net flows, emails, whatever. For the time being, we will just look at file system timelining. That's complex enough. And let's recall that most file systems, we have 3 types of timestamps for every file or directory. The mtime, modification time, which is when the content was changed, and the access time, atime, which is when the content was read, and the ctime, the change time, which is when the file status or file metadata changed. So, for instance, ownership or permissions or so. Sometimes there's also CR time, create times, most notably on NTFS and X4. But in general, you'll see MAC times. So this is called generally MAC data. The way to do that is, again, with system tools. The way to get all files MAC times is this nifty find command. That'll just loop over all the files in the file system, print them out to standard out. Xargs will take the files and put them in this stat query. Stat, again, in turn, just displays these parameters, which is essentially the dates, the ownerships, and the name. And you can write that into a dat file. I've already done that. And that looks like this. then. So these are the mtimes, permissions, owners, owner user ID, owner group ID, and the file name. And then you can pretty print that with a nice Python script. There's a 10-liner that'll just take stuff and make it readable, which looks like this then. And in particular, this is sorted now by timestamps. So you get a nice overview of what happened on this system. And so you can see on this particular system, some stuff happened at 2019, 12, 17. That's when apparently this was packaged, and it goes up to the latest entries. Well, last week when I put together this demo. So now you can actually look at when things happened, and this allows you to actually build retrace an attacker's steps. If you suspect that an attacker did something, then well, if he logged in, then he must have touched whatever files in the home directory, and then if he downloaded something, you can see that actually. If you compiled something, then you'll see some compiler files being touched in that general vicinity, time-wise. Of course, keep in mind that this command touches every directory. So depending on whether the image is mounted rewritable, then this might screw up all the access times of the directories. So keep that in mind. Another way to do this is use the sleuthkit tools. Another set of tools that is fairly easy to get. Very low line, but it's an additional set of tools. You can get the same information from a raw image instead of a mounted image. With this command here, tsk get times. This runs for a bit. I've already done that as well. And this looks essentially the same information, little different. Nice thing about this is it also can calculate MD5 sums on the way. And then you can use a different tool that comes with sleuthkit to do again some pretty printing. And here's the next pitfall that you can run into. There's plenty of times, as it turns out, that look like this. So there's files with date 0, invalid. Well, yeah, that turns out that those are invalid create times that the sleuthkit tools helpfully try to fill in, but they don't really help you in any ways. So you can just filter them out, which is what I usually do, and come up with this. I documented this as well. So you just set those lines away, and you have a nice CSV file of the timeline. So in order to make use of that, it's important to have some tool set to help you analyze this. This is more advanced, and we'll cover that mostly in next week. For the moment, I'd like to point you to a tool that I really like called Visidata. That'll just take any CSV data and display that in searchable format, and you can do lots of stuff in here. So this is really neat. I'd give you some more demo on this, but time is running out, and this is not really central. So suffice it to say that you can look around here and see, oh, look, what's happening here. Somebody has been installing Vim on this system. For instance, you can tell there's plenty of files that are Vim related, user share Vim 82, and they all have the same type, which is C, change, which can be interpreted in under circumstances with a caveat to mean create as well. Mostly it's technically not, but many times it's the create date, and that many files in one spot in time belonging to the same software package really, really looks like somebody installed Vim. And indeed, I did install Vim in this instance. So timelines, some observations that may or may not be obvious. Mtimes, so modification times, and access times can be changed trivially. You just have to access or modify the file. ctimes, change times, are harder to fake because many times you need to be root to do that. ctimes often, but not always, also indicate when a file was actually created, namely in all those cases where after that it was not change owned or change modded or anything after that, which is not guaranteed, but in many times it is identical. Atimes can help us in that whenever a binary is executed, its atime is updated because the contents were read, right? And many tools try very hard to preserve atimes and mtimes in their default mode. So rsync, tar, zip, all those tools try hard to keep those mtimes and atimes, which can also be of interest because if you can possibly, if an attacker say brings his own toolkit with him, then the mtimes maybe tell you something about when he assembled the toolkit at home, so to speak. So that's an interesting source of information as well. Some things to look out for. That's something that's surprisingly easy to forget is that all those timestamps only record the most current timestamp, as in whenever this timestamp was whenever a file was accessed or changed or modified before that timestamp, that is overwritten, of course. In particular, this means that whenever you do something like the find command on an initial investigation or just log in and browse while the system is still running, for instance, keep in mind that that simple act already changes at least some of the file system timeline entries. Also, cron jobs and stuff, scheduled jobs that run, say, every day or every week or every hour, obviously also screw up periodically screw up those traces and hints that are left by possible attackers. So be mindful of that. And of course, the time zone of the system is essential to know. Not for the sequence of events on the system itself, but to correlate it with external systems, say NetFlows or other logs or email servers, whatever. Any external source will also have a time zone configured and possibly the same, but you don't know. So it is critical that you know what your system's time zones are. So to wrap up, as you see, this is very, very, very tedious if you have to stab in the dark. There's plenty of files that you can look through and to no end, and you'll just go blind with going through timelines. Every clue that you can possibly get is a great, great help. So any indicators of compromise that can possibly provide any direction for your search will help a lot. And automation of this helps a lot, but it requires some effort beforehand, obviously. We'll talk more about automation in the next talk. There are sophisticated tools that will go a long way of helping you to identify traces, but those require way more effort than just running a find command. In particular, you need resources beforehand. The usual dangerous pitfalls that you can stumble over, not having found anything in a timeline does not mean there is nothing to find, because you overlook stuff. Everybody does. Even if you don't find anything, that doesn't mean that there is nothing to find. Because an attacker might actually be smart enough not to leave traces that are detectable by whatever means are at your disposal. That may be the case. And there's typically very few traces, in particular in the beginning of an investigation and in the early stages. And those few traces can usually be easily misinterpreted. So it's be aware that it's easy to jump to conclusions. And anything like a thorough forensic investigation will likely, very, very likely, take way more time than you're at least willing, possibly even able to invest in this analysis. So it helps a lot to have thought about beforehand what you actually want to reach, which goal you actually want to reach, what your final, well, destination, so to speak, is. Do you want to find out if a system is compromised? Is that good enough for you? Do you want to find out how? Do you want to look through the timeline, and if you don't find any clues, that's good enough for you? Or do you want to do the triage, and if you don't find anything in the usual suspects, that's good enough for you? Is it good enough for you if you take the indicators of compromise of a given advisory and look at those and see if those match, and if not, that's fine. All valid questions with valid answers. And the easier you can make your life, the better, because the fewer resources you'll be wasting on this. And this takes me to the last slide. Thank you. I suppose there may be questions. I've seen Klaus has already helpfully answered some in the chat. Let me go through the chat. Hello, setup. Yep, yeah. Of course.
Thank you, Tobias. I can't see anything which leaps out from the chat area. So yeah, I think Pascal, you had a question at the beginning. I don't know if that's still valid now.
I don't see any little discussion, but not many questions. Okay. So thank you. I'll stop my share.
Great. Thank you so much, Tobias, as ever. Thank you. Thank you, everybody, for attending. And I hope it's been useful. And like I say, we've got it recorded, so we will be able to upload it, and you can look at it at your leisure and share it with your colleagues who couldn't make it today. So thank you all, and you'll be glad to know you won't be listening to me next Monday. I'm off next Monday, but the next session is on next Monday. So I hope you all are looking forward to that, and I hope you enjoy it. Thank you very much.